Hi, Mr. Jackson. How are you?
Okay, how you doing, Brittany?
I'm okay.
Great. So yeah, you found the link. What I always do is, since I send it out both for both the classroom and for the office hour room, via Remind, I always go digging into someone's Remind.
Well, I was actually able to go to my email and I just clicked on Zoom meeting because I searched it and it allowed me to click on a link. So I was able to do it from there.
Okay, so you can see we start with Q&A today. And if you came in with any questions, happy to look at those before we go to the ALA.
Yes. So for 10.1, let me see. Let me go to my I had the link saved. Let me see. Why is it not open math? I probably can't stay the whole time, Mr. Jackson, because I have to go enroll my kids into school. I just got out from work. Well, we're transferring because we just moved. So I'm gonna try to stay for as long as I can.
Oh yeah, how did the move go?
I had movers, but it was pretty long. It was pretty long, but I made it through.
Yeah,
they moved all of my furniture and then I had to put everything up. I still have a few boxes left, but I'm almost complete.
Well, that's good.
Yes, sir.
That's disruptive for your work too.
Yes, sir. So I was trying to complete homework, put things up, finish getting moved in, go clean up the old house. It was a lot.
Yeah. Yeah, we moved in December. What a pain that was. Okay, so which question are you?
So I was sitting there last night trying to I was kind of lost. I took notes.
Okay. So like this one here, number 1.
Mm-hmm.
An anthropologist finds skeletal remains, they need to figure out the height of the person, the height of a person in centimeters, and the length of the metacarpal bone were collected for 18 sets of skeletal remains. The data are in the table below. Okay, so they just say it like it's not important, but it's really important here where they say the anthropologist needs to figure out the height of the person. So you're starting with kind of an explanatory variable x. It's like algebra, x, y.
So we would put those into the calculator, like x into L1, height into L2.
Yes, that's going to happen. Now we have to state the random variable. So we have to figure out the height of the person. So let's see what the choices are here. Random variable x is
going to be the length of the metacarpal, right?
Right. You got to be careful because sometimes two of them are almost the same. Length of metacarpal. See, now that sounds right. Not the mean. Yeah. Okay. Of. Oh, okay. So yeah. Of a set of skeletal remains. A randomly selected set of skeletal remains. And then Y is the height
Yes, so, okay.
of one set of skeletal domains.
Oh, so we'll just say the height, okay?
I guess that's what they want. Let's see. Mean, no. All, no. Length, no. Random, it's not. Randomly selected set. No, Y is that person's height. And then for a set of skeletal domains. Remains. I would say domains.
Okay.
Okay, so make a scatter plot of X versus Y in StatCrunch or on your TI-84 calculator. So here's where we input all of our data.
I'll name them out for you as you type them in.
Oh, great. So stat, edit. I'll just type over. Go ahead.
Okay, 46.
46,
48,
48,
45,
45,
42,
42,
50,
50,
51.
61,
No, 51, 51.
51,
50,
50,
41,
41,
48,
48,
46,
46,
47,
47,
45,
45,
40,
40,
43,
43,
another 43,
43,
49,
49,
40,
40,
and 47.
47. Okay, so 18. Yeah, 18 sets of domain or remains, which it says
skeletal
right
remain.
here. So we're checking that. 18, 18, that matches. Now we're going to go to the top of list 2 because these are ordered pairs, and each row of this table refers to, the same individual. And
Okay,
you cannot mix up the order. So the 46 has to go with the 169.
okay. 174,
174,
173,
173,
165,
165,
178,
178,
180,
180,
181,
181,
165,
165,
171,
171,
175,
175,
another 175,
175,
173,
173,
155,
155,
177,
177,
170,
170,
another 170,
170,
163,
163,
and 172.
172. And so we did have the right number of data, which is important to check that. And fortunately, when you're reciting the data to me, I can be checking to make sure, the inputting is believable. You don't necessarily have to check every input value. You should at least scan and look at to make sure you didn't have an individual that was 1,700 centimeters tall.
Okay.
Okay, so we got the data in there, and they're asking for a scatter plot. So, and we may or may not use our scatter plot to answer the question, or we might use it and then look at some individual data which kind of help pick one of them. So second Y equals is stat plot. Let's use plot 2. X list is L1, Y list is L2. We have to select scatter plot, which is that one right there.
Mm-hmm.
And then the window, this part is important because, you know, I could just hit graph and I probably won't see any of the data. Okay. Yeah, because the numbers are too big. So, oh yeah, well, I see a curve there
Mm-hmm.
that I'm just gonna get rid of. But to get a good window, we're gonna go zoom, and then 9 is zoom stat. And so they'll give a window which fits the data. It gives you a good picture. Got the data.
So after we put all of our L1 and L2 in, we'll go to zoom and then zoom stat.
Yeah, I think what you have to do is, okay, that's on. Okay, so then y equals, okay, plot 2, window, oh, zoom 9 is zoom stat. So it should give us a window which is good for these data. Okay, so, okay, now we might be able to match it. It looks like that bottom one there, because you see that those 3
Mm-hmm.
in the upper right. So it looks like this bottom one here. Let's see if it matches in the other details. Like this one almost wants to be like that. It'd be nice to have something else which we can use to confirm this one instead of this one. I mean, we're pretty sure because that little cluster of 3 data, it looks like it wants to be this tight cluster here instead of this loose cluster up here.
Mm-hmm.
Otherwise, everything else is exactly the same. So now, let's see if this view helps. And let's see. Well, I think I think we're good because there is scale that would be violated that if it were this loose triangle up here. So I think we're pretty good with
Okay, the last one.
yeah, the bottom one here. Let's see. And oh yeah. Yeah, that was it.
Okay.
Find the equation of the best fitting line, the least squares regression equation. Rounding round to 2 decimal places. So let's see. We'll go linreg. So stat, calc, and linreg, x plus b. That should be good.
So you went to stat, cal, and then linrig.
Right, 4 is linreg.
And then you have to enter X.
We got the list 1, list 2. We don't need a frequency. Okay, so they give us a regression equation. And it looks believable considering, you know, our variables, length of a metacarpal bone, whatever that is. I don't know what it is, but it would seem that any bone would be able to predict height with some accuracy. You know, taller people have longer bones. So now
So those two would be our decimals, the A and the B.
Right, so, and of course, they're saying that the regression line, it's a line. So if you remember from algebra, a line has an equation of the form y equals, usually they say mx plus b in algebra, but we say ax plus b in stats. And so this value of a here is going to go in there for a, and this value of b is going to go in there for b. And so we have y equals 1.448. Let's see. It says round to 2 decimal places. So we're going to say 1.45, but I feel like we might end up using these numbers again. And if so, we might be required to keep all of the accuracy we, can get. 4483929.
So it'll be 1.45.
Right. X plus this number, 105 and change.
105.47.
Yes.
Does it matter how we put them?
You mean if you put them with more accuracy rather than less? I think mom would.
No, so like how they have the equation y equals, can we put 1.45 plus 105.47?
Oh, no, the constant has to be by itself, and the coefficient of x has to be, next to the x multiplied by x. So we're going to switch the order of the numbers.
Oh, I see what you're saying.
Yeah.
So 1.45 should come in the second box because
Right.
the coefficient is x.
Right. 105.47 plus 1.45. Okay, so let me confirm that's what they wanted. Oh, they're getting a slightly different. They're saying y hat. For the model. Now they're saying so just slightly different regression line. I wonder if we made an inputting error. I don't see one yet. Okay, yeah, that's right. 170. Okay.
I'm putting it into my calculator too.
Yeah, I mean, it's close, but it's not the same. Find the equation, best fitting line, least squares regression equation.
77, 170, 170, 163, 172. Oh, wait.
Is yours different?
Oh my goodness. I messed up, Mr. Jackson. Hold on. Okay, 169. I'm doing this L2, 174, 173, 165, 178, 180, 181, 165, 170.
Okay, now, now I've got the same as mom.
You do?
And so means I have to fix it over here. But what I did was I took off the frequency list L2. And then for some reason it turns out to be the same. One point.
Oh, okay, because you did say we don't need a frequency.
Wait a minute.
Yeah, that's what I got too. I got the 1.469, so there should be 1.467. I mean 1.47.
Yeah, yeah. 1.4
And then
9431726.
okay, so 1.469431726. And then for B, I have 104.4220307.
Okay, well, good.
So it should be 104.42 and then plus 1.47 times X.
Again, this is a win for StatCrunch. Now, it's not required, but to copy and paste the data not only saves time, but saves errors. 104.42. Okay. Restricted domain. So let's see. X. Now this is a compound inequality. X is between. And I think what they want is just the least and greatest values from up here. Now, in theory, the inequality would have, in theory, you could say 0 because you can't have metacarpal bone, which is negative in length. You can't even have one that's 0. So strictly greater than, and then X, and then less than or equal to. But because there's an upper bound on the interval here for the domain, I think the point here is that we should only expect this regression line to be, worth anything as far as prediction goes within the range of the data, I should say the domain of the data. And outside the domain, we couldn't expect this regression equation to predict anything well. In that case, we would be guilty of extrapolation And we don't want to do that. So the min and the max values here are what we're going to have for our restricted domain. So the greatest X value and the least X value. The least X value is 40. The greatest X value is 51. So just, you know, looking at it up here, the least value is 40 and the greatest value is 51.
Okay, so that's what we go, let me see. Oh, so they want the greatest and the least and the greatest of the X value.
Right. If you remember from algebra, the domain is the set of X values. Interpret the slope from part C in the context of this problem, okay? Now the slope I'll just write the little slope is approximately 1.47. Okay. And so the interpretation of that is for each increase of one. See, now this is why they're saying pay attention to the units. What were the units for the metacarpal? Centimeters. They're both centimeters. So for each increase of 1 centimeter in the metacarpal, I guess that's like near your heart, metacarpal. We can expect 1.47 centimeters increase in height.
Okay, we can expect the height to increase by 1.47 centimeters.
Yeah, so every time we increase the length of a metacarpal by 1 centimeter, we can expect an increase of 1.47 centimeters in the height. The height to increase, because it's positive number, 1.47, by about 1.47 centimeters on average. Makes sense, Brittany?
Yes, yes, sir.
Great.
So where did you get your 1 centimeter from?
Well, this 1.47, you know, it's like a slope, right? So it's 1.47 over 1. So rise over run.
Oh, okay.
Yeah.
Rise over run. Got you.
This is why we did all that stuff about linear equations, linear functions in the foundations class.
Got you.
Interpret the y-intercept in part C in the context of this problem include units. So now we're going to interpret the 104.42.
So that's going to be
now a y-intercept is a 0.0 something. 104.42. And so that's saying that it's an interpretation which is kind of detached from reality, because it's like if you had someone with zero length metacarpal, then we would predict that that person is 104.42 centimeters tall.
Mm-hmm.
I don't know if that's possible, not to have a metacarpal bone. Every time we increase, okay, so y-intercept, when the length of the metacarpal is 0,
And then the 104.42 would be the length of the metacarpal is 0 centimeters. We expect the height to be 104.
0.42, right? The height,
Centimeters.
does it make sense to interpret the y-intercept on this problem? No, it doesn't make any sense. We don't think, we don't really know what a metacarpal is, but do you know what it is, Brittany?
The metacarpal?
Yeah.
Isn't it like a bone, like in your like the joints or something like that?
I don't know, but I'm just, it could be,
I remember learning that in medical assistant school. I just forgot.
okay, well, I'm betting that it doesn't make sense because no one has a metacarpal bone length 0. So let's go with that. So no, since, oh, okay, well, there you go. It's 0 is out of the domain anyway. So that's excellent. So 0, x equals 0 is not between the x min and the x max. So no. So that's, yeah. Even if it were possible, the model, this model right here, would not be useful for prediction.
Mm-hmm.
Because it's not in the range that is, makes this prediction regression line legitimate. Should you use the regression equation to predict the height of a randomly selected set of skeletal remains that has a length of metacarpal of 45? Yeah, I believe so, because that's right. That's in the interval, right?
Mm-hmm.
The interval is 40 to 51, I believe. And so it's kind of like that interval goes with this regression line. It's kind of like the fine print. This regression line, y hat, is useful provided that x, the length of the metacarpal, is between 40 and 51. So that's a yes on part F. Yes, this x value is between the x min and the x max. Should you use the regression equation to predict? Now they're saying 61. So what do you think about 61?
Should you use the regression equation to predict the height of a randomly selected skeletal remain that has a length of metacarpal of 61 centimeters?
Yeah.
No, because it's between the 40, what was it? The 40 and 51.
Right. Exactly right. Looking at your answers above, predict the height for the one above that it made sense to do so. So that person for whom it made sense to predict the height is the person with length of a metacarpal of 45. Didn't make sense for the 0, didn't make sense for the 61,
right?
Makes sense for the 45. And so then the predicted height of that person is, let's see, 1 point. I halfway expect them to say don't use your rounded numbers, but they didn't say that, so I'll go ahead and use the rounded 1.47, and then the X is 45, and then plus the 1.422.
Okay. So hold on, wait, you got Y hat 1.47.
Times 45 plus 1.422.
But where would we get the 1.422 if it's 104.42?
104.
Is that what we, yeah?
No, yeah, thank you for correcting my mistake there. 104.42. So the
Let's see.
prediction for the height, assuming that we are allowed to use those rounded numbers, is 170.57. centimeters. Let's see. Make sure you use, oh, they did say that. Okay, fine. Make sure you use the stored equation, not the rounded one. Okay, so I thought they,
Oh, so we have to use the one that we got before we rounded.
right. Okay, so let's bring that back. Well, let's just go back to the
So I should have Y hat equals 1.4694317226 plus, oh no, times.
four, 6, 9, 4, 3, 1, 7, 2, 6.
And where did you get the 45 from, Mr. Jackson?
Because they said
Looking at your answers predict.
they said looking at your answers above, predict the height for the one above, that it made sense to do so.
Okay.
So it made sense to do so with the 45, not with the 0 and not with the 61, right? Because those were out of the
Oh, okay, I see what you're saying, 45, okay. Plus 104.4220307 equals. Okay.
plus 104.220307. Okay, so with the, so instead of 170.57, it's 170.5. Are we supposed to round this answer? Yes, to 2 decimal places. 170.55, right, Brittany?
I'm trying to do it. Hold on, Mr. Jackson. I got an error.
Okay, did you multiply by 45?
That's what I did. I put 45 in parentheses and I think that's what got me. Plus,
Well, that which should be okay.
right,
As long as you multiply.
4220307 equals. And I got 170.5464584.
That's right.
Round to 2 decimal places, it's gonna be 170.55. Is that what you got?
Yes.
Okay.
Okay, so predicted height 170. Length of metacarpal is 45. The predicted height for randomly selected set of skeletal remains that has a length of metacarpal of 45 centimeters is 170.55 centimeters. Compute the residual for the following ordered pair. Okay. Okay. Now, residual is y minus y hat, I believe. Residual. Y minus y hat. The actual value, or the actual value minus the predicted value. Now, I'm going to confirm that it's y minus y hat and not y hat minus y. I'm pretty sure that's right, actually. So now we're going to do the same thing with 48. Okay, so
Are we using the same numbers?
the same regression equation. This is observed, and y hat is the predicted.
And we're just gonna subtract instead of adding and multiplying?
Well, we're going to do the same thing. So we're going to put the 48 in here, okay, and get a number for that. And that'll be the predicted. And then we're going to subtract that from the actual observed height of 171. So it's going to be 171 minus whatever we get from the calculator.
Okay, so do it exactly how we did it. 48 plus.
Second enters entry, replace the 45 with the 48. Get that.
Did you get 174.9547535? Oh, yeah, that's what you got. Round to 2 decimal places, right?
I think that's likely. So this is going to be negative 3.95. The residual, okay, so let's hope this is negative and not positive, and that I did remember correctly. Y minus Y hat is what the residual is. Residual, yeah, is, yeah, negative 3.95 centimeters.
It is negative 3.95 centimeters. Okay, so CM and negative 3.95.
So on the scatter plot, there's going to be a place where the regression line is 3.95 above the actual. So the 148, 171, let's get our, okay, and let's find it. So I'm going to hit trace. So 48, let's go find that. It's not that one. It's, okay. Oh, it goes through the data in order. Okay, so 48, 171. So it's that person right there. Okay.
And what did you go to?
I just hit graph and then I went trace, which is the fourth button.
So graph and then trace.
Right. Now you can see how that's a little bit lower than you might expect. And you can feel a regression line that goes kind of like this. Now we could actually graph it, right? Because we have the coefficients of the line, but the regression line is going to, be something like this. And that observation is a little bit lower than we might expect for an X value of 48.
So wait a minute. Okay, so before you did the graph and trace, because I was still writing down some information, did you go back to stat and then the L1 and L2?
No, I just, okay, so I went to graph and then I went to trace, which is this fourth button right here. Okay.
Mm-hmm.
And then if you use the left and right arrow buttons, it just hops between, I guess, in order of the data. And we had to go through several data before we got to the 48, 171. And
Okay.
it is a little bit low. So this person's, slightly shorter than predicted. The actual height of a randomly selected set of skeletal domains and the length with a length of 48 centimeters. Okay, so the actual height of 171, which is 395 below what was predicted. Well, I should just look at before I put below, I should just look at the centimeters, yeah. Below. Oh, it is below. Okay. And, I'm sure you're fine with this eyeballing of the regression line.
Yes, sir.
Okay. So again, we could go to y equals and we could input it and get a graph on it, and it'll, cut through the way we were showing. Anything else I can do for you?
No, sir, that was it. I shouldn't have any trouble doing the rest of them. I was just like, I was really lost.
Okay, good. So we'll look at this. This is now taking this two variable thing that we're doing in chapter 10, which is different, right? I mean, this whole book, we've only had one variable, X, and now we've got two variables, X and Y. And now we're going to say, okay, here's a scatter plot, and how good is it? You know, do we think that there is actually a relationship between length of a metacarpal and height? Now, intuitively, we think there is, because, you know, because in our experience, someone with longer bones is going to be taller. But then here's a way to test that, because you have two other things that you think, and I'm not sure if those are dependent on each other or whether they have a relationship between each other. Sometimes it's not so clear. So in that way, we can get the we can get a scatter plot. We can also get a statistic known as the correlation coefficient R. Now, there are a couple different ways to get R. And, you know, what is R? Okay, so that kind of goes to the first question here, which I'm curious to see whether anyone actually answered, because there's R and there's rho. Now, rho is a Greek letter, and so, as is usually the case, it's not a P, that's not a P, it kind of looks like a P. We don't need any more P's in statistics with all the P's that we've had. You know, it's
probability.
Yeah, it's more like R. And so there's rho, the Greek letter, which Greek letters generally have stood for population parameters, whereas regular, you know, letters that we have in English stand for sample statistics. So again, the alliteration, population parameter and sample statistics, you know. So sample statistics, we have things like, you know, X bar and S and R. Those are sample stats. Rho is the population correlation coefficient, not to be confused with the sample correlation coefficient. So that's what I mean down here when I'm asking, is R the same thing as rho? No, it's not. One is for the sample, another thing is for the population. I agree with Brittany's statement. Yeah, that's right. 1, -1. Okay, so no one really said what I was hoping to see here, which is that rho is the population correlation coefficient. Now, you got part of it. What you said is, you know, good as far as it goes. But the important thing that I was going for there is that it was for the population. Now, you mentioned the 1 and the -1. For a perfect positive correlation and -1 for a perfect negative correlation. If you have a perfect positive correlation, then all these points are going to be lined up perfectly in a line. If they're lined up perfectly in a line that goes downhill as we read from left to right, then that's a perfectly negative correlation of -1. This one is more positive than negative. We had this, I drew this eyeballing of the regression
Mm-hmm.
here, and it goes uphill as we read from left to right, which tells us that the value of
It's going to
R
be positive.
is going to be positive. So what is it exactly? Now,
So if it were to be going like where the scatter plot was the opposite direction, it would be negative, right? Because it could either go
yes,
left or like down leftward.
yeah,
Okay.
down as we read from left to right.
Okay.
Yeah. Now, there are two ways to get R, and one of them will come along with the hypothesis test that we do in 10.3, which is a Lin-Reg t-test, which is here. So stat tests, and then a linear regression t-test F. And so they're going to give us,
And that's what we use today, right?
well, yeah, that's what we're going to use to decide on the null hypothesis rho equal to 0.
But okay, so will we always not have a frequency?
Well, frequency is not really it's not a concern in chapter 10
Okay.
because we have two variables instead of one variable X and then maybe some different frequencies for the different X values.
Okay.
So you can see on here that rho not equal to 0, which is good, which is always our null hypothesis in 10.3.
Okay.
So the null, or I'm sorry, the alternative hypothesis. The null is always going to be rho equals 0, right? Because the null is always the hypothesis of equality. And then for the alternative, it's always a not equal to.
Okay.
But we're just here at the moment to get the value of R, because looking at that scatter plot that we just saw, I would guess that the value of R is going to be positive 0.9 maybe. Let's see. Now you have all this stuff, all of which is important. We see our regression line in there. Oh, R is closer to 0.8. Okay, so I went a little high on R, but that's the value of R. And yeah, I believe that. These data, they're not perfectly lined up. And that kind of says about how not perfect they're kind of lined up. They're 0.8 worth of lined up. What keystrokes can you use to find the value of R? So we just did it one way. Let's see if anyone answered that. Someone gave a formula for the test stat Z, which is not what the question is, but it's nice to know. I guess that's times right there. R is always between -1 and 1 inclusive. Yeah. I mean, we had that on the previous slide. Okay, so that's nice. So we gave one way to do the keystrokes to find the value of R. And I won't even confuse the matter with the other way unless, a need for it comes up. So we use The keystrokes are going to be stat, tests, linreg t-test.
Okay, so
Stat,
I want
test,
the calculator. So you did stat, test, linreg, okay. T-test, not interval, right?
right, right.
Stat, test, linreg, test. Okay,
Okay, so it's interesting. Rio throws out all this stuff. And then she shows that she knows how to get the right keystrokes. I assume they're right. To get the value of R. So she got a value of R. And she correctly remarks that there's a strong positive linear correlation or linear relationship between X and Y. Now, she didn't do the other part, which was determine whether there would be a linear relation, whether the null hypothesis of rho equal to 0 would be rejected between X and Y. So let's confirm that value of R. Stat, edit, clear the list, clear the other list.
okay, Mr. Jackson, I'm gonna go ahead and go to the school so I can go register my children for school.
Okay, Brittany,
I'll see you later. Thank you so much.
my pleasure. Yep, have a good one.
You too.
So for the recording, let's check on this value of R. Put our X values, 2, 4, 6, 6, 7. Four, 8, 10, 13, 20. And we're going to go to the linreg t-test, which will not only do the first thing, but also the second thing. It'll tell us R, and then it'll tell us whether we're going to reject the null hypothesis of rho equal to 0. Because again, the hypotheses are rho equals 0 and rho not equal to 0. Tests F linreg t-test. This one, this two, yeah. Not equal to 0 is the alternative. So rho not equal to 0, rho not equal to 0. That's a rho right there, a Greek letter. It's not P. So we have a regression line. We have a test statistic. So sometimes you're required to give that. The value of the test stat T which is 3.49. Now that P right there really is P, and it's a P value. So, and it works like all the P values that we've had in the course up to now. So 0.0397. Now, well, let's check on her value of R and confirm that that is correct. Yes. Now, how do we do that second part? How do we determine whether there would be a linear relationship between X and Y? Well, in the past, what we've always done is we have taken our p-value and asked, is it less than the level of significance alpha? But they don't give us an alpha. And so if they don't give us an alpha, we always use alpha equal to 0.05. And this number is less than that. So reject H null. And we conclude that there is a linear relation. There is a linear relation. Because what does it look like if there's not a linear relationship between X and Y? Well, it's going to look different than this. Let's get our scatter plot here. Again, if we hit graph, our scatter plot, let me look at this. Y equals, okay, plot 2. I think we're still using plot 2. I could hit graph, but we're not going to see our points because our window's off. Now we've got small data. So let's just readjust the window by again going zoom and 9, zoom stat. Okay, so they're kind of lined up. They're lined up pretty well. What does it look like when you have that kind of situation of the null hypothesis, rho equal to 0? There's no correlation. Well, then you just got data kind of like scattered all over the place, and there's like nothing you can make out of that. That's totally not what we have here, which is that our data here are pretty well lined up. Now, this is P reject or no reject. So this is back to 7.2, I believe, which is the proportion. So we're testing the population proportion P for its value, whatever the problem situation says. And so we're running kind of the old kind of hypothesis test, and we're going to reject P equal to a number given to us in the problem, or we're not going to reject it. What is the P for which we are testing? Well, one person said this, but that's not it. This P, for which, the one for which we are testing, is different than the P value. And then Rio comes along and says, yeah, P is the population proportion, which is exactly right. how is Z computed in testing for P? She gives a formula, okay? Okay, so notice the form of it is pretty much like x minus mu over sigma. Gonna do a little correction on this. That radical symbol should be all the way down to so that the n is actually in there too. How do you use Z to get the p-value? By using the one prop Z test. I'll buy that. What we used to do is say, okay, here is the distribution. It's a Z distribution, and you have a value of Z here. We'll say Z null. Well, let's just say Z. Z1. And let's get rid of this. Okay, so in that value of Z determines an area. Okay, there's an area. And if it's a one-sided test, you know, if it's, for example, okay, so the null is, you know, P equals whatever, and the alternative, oops, is P greater than. So a one-tailed test. Then this area in the right tail that is the p-value. Area equals p-value. But what we do is really instead, and this is stats with tech, Kozak. So yeah, we use a one prop Z test to get a p-value. That's correct. Given the p-value in alpha, how do you make a decision about the null hypothesis by comparing the p-value to the level of significance? Well, yes, but which way? If the p-value is low, the null must go. So if the p-value is less than alpha, then you reject the null. So which way? P-value less than alpha, or p-value greater than alpha. So the null there on number 7 is P equal to 0.3, and it's a one-tailed greater than the P hat here is X over N, which is 75 over 200, which is 0.375. So that's quite a bit bigger than 0.3. And so no surprise here that we're getting such a small p-value, such a large value of z. She's totally nailing this, so I'm sure this is right. 2.31 feels exactly right. And a p-value, which she even drew the picture with the area and the table, the one that I just drew. A p-value that's low, so the null must go. Excellent job. So the intention here is that we're going to get into a rhythm here. Let's see. Yeah, so this is interesting. We have an alternative, which is a not equal to. Therefore, we have a two-tailed test. And we're starting to get into a rhythm of deciding yes, we reject, or no, we don't reject, based on is the p-value low. And everything here looks good. Now we're at 7.3, doing a t-test for mu, the population mean. Okay, perfect, perfect, perfect. We had a question on 6.5. We have a question from 6.5. sampling distribution of the sample mean. Random variable X is not normally distributed. It has a mean of 46, standard deviation of 4. So mu is 46. Mu is the population mean. And sigma is 4. Population, standard deviation. If you take a sample of size 24, so now things get interesting. N equals 24. Can you say what the shape of the sampling distribution for the sample mean is? So that's a formula already used in this little segment that you have to know and really memorize. The sampling distribution of the sample mean. Okay. So the X variable looks like this, but sample size 24. Now, if it were 30, then we would just say normal. But because it's less than 30, we're saying no, we don't know the shape of the sampling distribution of the sample mean. Why or why not check all that apply? Population is not normal. That is critically important. And it says that, yeah, not normally distributed. N is at least 30, which is not even true. Population is normal. That's not true. N is less than 30. Yes. And sigma is known, but I don't think that matters. Sigma's being known or not known matters. But not here. For sample size 24, state the mean and standard deviation of the sampling distribution of the sample mean. Okay, well, the mean of the sampling distribution of the sample mean, that's going to hang right there at 24. Or at 46, I believe it was. But the standard deviation of the sampling distribution of the sample mean is going to be not that, I think it was 6. Not 6. Oh, 4, not 4. But it'll be sigma divided by root n. Sigma divided by the square root of n. because we're talking about the sampling distribution of the sample mean. A big important thing that we're talking about. So by the central limit theorem, sigma over root n, which is 4 over the square root of 24, which is this number, which is approximately 0.82. You take a sample of size 45, can you say that the shape of the distribution of the sample mean is? Yes, in that case, it's going to be normal. And why or why not? Population is still not normal, but that's not a reason why we're going to say that the sampling distribution of the sample mean is now normal. So n is now 45. Now we're going to get this nice bell-shaped curve for the sampling distribution of the sample mean. What's the sample mean? X bar. So this is a distribution not of x's, but of x bars. The mean of that distribution will still be 46 because the mu of the x bars is the same thing as the mu of the x's. But of course, according to the central limit theorem, the sigma of the x bars is the sigma of the x's divided by square root of the sample size. Let's see, and so if n is now 45, we couldn't say it's less than 30, it's at least 30. Population is normal, no. Sigma is known, yes. And some would argue that that is part of the reason why we can say the shape of the normal distribution or the sampling distribution of the sample mean is normal. Let's see if they can say that. Sigma is known. Okay, so not only can it be argued that way, but this question writer, evidently following Kozak, says yes. For sample size 45, state the mean and standard deviation of the sampling distribution of the sample mean. The mean, well, we know that's going to be 45 because of this. Or I'm sorry, the same is 46. 46, the same as the mean of the population, the same as that thing. But the standard deviation, according to the central limit theorem, okay, so in 6.5, you'll see a statement of the CLT. Also in the ALA, the CLT with one die, it has the, well, these two important equations are, you know, the heart of the central limit theorem. As I remarked in the ALA, the CLT with one die, the statement Kozak has in section 6.5 of the CLT is weird. It really should include these two equations as it does in the definition linked in that ALA. So sigma divided by root n, 4 divided by square root of 45. Second, enter his entry, edit the expression there, call it 45. So there's our new standard deviation of the sampling distribution of the sample mean. 0.5963 to 2 decimal places, 0.60. 0.60. Learn by doing. Eventually, mastery matters. Hope you found this helpful.